Good morning, everyone. Good morning. And thanks for joining AI in the battle against fakes. My name is Henk Boelman, and I'm a cloud advocate at Microsoft. But the story I'm going to tell you today dates back from the time that I was not a cloud advocate at Microsoft, but I was working as a cloud solution architect for a company called Heroes in the Netherlands. And our company back then was asked to create a solution that was able to detect counterfeit products. Meaning that you take a picture from my box where the product is in, run it through our engine, and it would tell you, hey, this product is counterfeited, or hey, you have bought a genuine product. So the agenda for my talk. We're first going to zoom into the assignment and the challenges we had. We're going to dive into the solution architecture, like which components I used in Microsoft Azure. And then we're going to zoom into two very specific components. We're going to zoom in how we use custom vision in a real-world scenario and how we used Azure Machine Learning Service to create custom models. And then afterwards, we will do a small recap. And of course, I have some lessons learned from this project. So first, the assignment and the challenge. So almost every AI and machine learning project starts with formulating a question. And in this case, the question was, is this a genuine package or is it a fake package? So the product or the solution we were making has to answer if this picture comes in, if it is fake or genuine. And for that, for every machine learning project, you need a lot of data. So we thought we would get like thousands and thousands of pictures of good images and thousands of images of fake products. But when we started the project, we asked like, can we have the data please? And the answer from the client was, yeah, sorry, we don't have any data for you. We just have some little pictures. And we were like, yeah, you're joking, right? So we had to find another way. So let's dive in a little bit into what the problem area was. So we have three pictures here of the same box. And only one of them is real. So I'm going to do a show of hands and see if you can detect the real product. So who thinks number one is a real product? Two. Number two. A little bit more. And number three. Okay, so 2 and 3 are about the same. So I will zoom in and I will show you which product is the real one. But 2 is the real product. And why? So we have to zoom into the little details. And can you see now why the difference between these two logos? Who can see it? A few, yeah. So it is this small piece that makes it real or fake. So yeah, we had like a big problem because you need like so much data to create your machine learning model. And even if you look at the small icons, like it is just a matter of the light that can be blurred out or this little bit of difference in the icon. Because when they make counterfeits, they might not have access to like the real icons. So we had to rethink this project. Like we thought it was going to be easy. Get a bunch of data, run it through this machine learning algorithm, and we would have our solution. So when we started studying these small differences and these small things the counterfeiters could fake, we decided to break the project up in like lots of smaller pieces and look at very specific things on the box. So the solution architecture. So we decided to create 3 separate areas, components for this application. So we have a management tool where the client could manage all the packages because there are like 1,000 different packages. So they all had to be uploaded and configured. There is a front end that the client would use all over the world. So from China to Australia to America. So it has to be very scalable. And we have an AI engine. And that is actually the engine that will analyze all the small details at the picture and at the box. And we used some ingredients from the Azure stack for that to do that. So we used Azure Durable Functions. So Azure Functions are our serverless offering that can kick off like small pieces of scripts. And Durable Functions is an extension on Azure Functions, so you can run and share state between multiple functions. So you can create a workflow of functions to orchestrate your solution. And that is what I needed, because I had a lot of different components that tell you small things it sees on the box. But we'll dive into that later. I used Azure Machine Learning Service to create our custom models. And where possible, I used Microsoft Cognitive Services because, yeah, they work out of the box and why reinvent the wheel. So my custom models I had to deploy in Azure Kubernetes servers, wrapped in Docker containers, control the API management because not everything runs in .NET and I had to run Python. And I stored all our data and configuration and results in Azure Cosmos DB. And we use blob storage to store, of course, all our images and log files. And then there is a little bit of a strange thing. I used Umbraco for content management and for configuring the projects. So let's zoom into a little bit at the configuration and what the content management system does. So we have 1,000 different products, and the client has to configure and upload all the products because we only want to tell if it is a genuine or a fake if the product is in our database. So they log into Umbraco, create a product, tag a product, say, hey, this is from this type, and we will see some more details later. And they had to upload one image of the front. And on that front image, we run our own AI engine to check for all the components. We detect, for instance, logos, icons, and all other small details. And we save all those configurations in Umbraco. And then, because I wanted to have it like loosely coupled, on the publish of the configuration, we push it to Cosmos DB. So later on, we could always replace Umbraco. And this is how Umbraco looks. So on the left, you see a list of products. You see a front image, so the boxes can also look like that. And then you see that we save all kind of details from the image, like the width, the height, the position of the logo, the position of the tag type. The tag type in this case is like the T2W. And for instance, the range type is original equipment. So we know where all the things are on the box and where they're supposed to be. And we run a scan that will detect all our icons and other things on the package. We save that in the configuration and we push that to Cosmos DB. So if we zoom into the AI engine flow, it is a chain of Azure Functions. And this is really simplified because we have like a lot more than that you see on this picture. So it all starts with an incoming photo. It's put on a storage device, a message is being placed on the queue, and the Azure function goes off. And the first step it does is to pre-process the image, meaning that it will look at the image, it will rotate it, adjust color balance, scale it back because some smartphones make like 10 MB photos and we actually don't need a 10 MB photo to run through our neural network. And then the second thing we do, we run an OCR on it and we try to see if we can match the product to a product in our database. And some of them, those products are really easy because there is just a product number on the front, and some of them are really hard and we have to detect the shape, see which and match range types and product types, and then come to a verdict. So it can only continue if we have matched it in our database, and otherwise we throw the message like, yeah, sorry, we don't know this product. Try again. So another thing we run when we have matched it, we run a text AI. And we use for that the computer vision API from Microsoft. And that can extract all the text on an image for you, tell you the bounding boxes of the text, and you get all the lines and where it actually is. And we also have that in our database, in our configuration, so we can just match, does all the text make actually sense, and is it on the right spot of the product? We run it through a logo classifier that classifies if the logo is actually a genuine logo. We detect multiple icons. We validate if those icons are genuine. And we do a lot more, which I'm not allowed to say because I'm not allowed to train you to be like the perfect counterfeiters. And then we do an end evaluation of all those different outcomes of those Azure functions. And we say, hey, this is a fake. We're not really sure, try it again, or hey, you have a real product. So all those Azure functions are there to orchestrate. And they call out to APIs that run in Docker containers. And those APIs run in Docker containers are self-sufficient components. They're not aware of the whole solution. You just send an image, and for instance, it detects the icons. Or it is an API that just validates the logo. So you can test those things all individually. And those Docker containers can call out to other cognitive services or other APIs that are needed. And the good thing about that is that all these Docker containers can have their own life cycle. So we can test them individually, we can deploy them, and improve on them to make the solution better without redeploying the whole big beast. So let's zoom into the icon detection and validation part. So this is the component that actually runs in the Docker container. So it is all written in Python. So this Docker container gets as input, the API running in the Docker container, gets as input this image. And it will run object detection on it. So it will detect where all the icons are. When it knows all the positions, it cuts those icons out. So we have like all different images. And those images we can run through specialized classifiers that will actually tell if it is genuine or fake. And that are classification models. So they will say, yeah, I'm like 95% sure that this is fake. So we can play with the threshold what we accept as a genuine or fake image, a fake icon. And then it just returns a JSON file telling like, hey, we found a car icon. It is genuine. And yeah, we're 95% sure about that. We can also detect only icons, like this hologram thing. So we only look for the presence of that. We don't validate if it is like fake or genuine, because with the reflections on these shiny things, it is really hard to train a good classifier. So how does it work? How do we train those models? So first we need, of course, a sample data set. So we have a sample data set of like a few thousand of boxes. And then we had an intern that had to tag all the icons. So he was busy for that for 2 weeks, just taking bounding boxes around icons. And we did that in the visual object tagging tool for Microsoft. So you can download it. I think it is an Electron app, so it will run everywhere. And you can start tagging, and it will save the output in a JSON file. So you can later on read it in every program and recreate it. But there is also an export button, and that will upload all the images with all the coordinates to the Microsoft Custom Vision service. And that Custom Vision service is a fully managed service by Microsoft where you can just upload your images to, hit the train button, and it will create a model for you. And you can configure that. So you train the model, and it can also deploy and host that model for you. And then we have some Jupyter notebooks with our test cases, and we run that against the API. And we'll see if our model improved on our test set or was getting worse. So that was object of icon detection. So this still doesn't say if the icon is real or not. It doesn't see the very small difference. It just finds icons for you. So for verification, that is actually way easier to train, and it takes less effort to do. So we created a Jupyter notebook, and we have the images in 2 folders. So we have genuine icons and fake icons. And we do a lot of image augmentation on that. So we rotate all the images, we change backgrounds, we change colors, because our boxes are in all different colors. And the photo doesn't necessarily have to be straight. So we do a lot of that. And then we upload them to the Custom Vision Service API. We train the model again, deploy it, and we test it. So if we zoom in how this icon validator API looks like, there's a Docker container running Python 3.6. It is on a very small Ubuntu image, and it is a Docker. And so it calls out, when an image comes in, it calls out to a lot of different custom vision models. And the good thing about that is that every model we can train and maintain individually. So if our classification model for the car is not performing that well, we can individually tweak it without redeploying even the container. And they, of course, have their own data sets, which we can maintain separately. Our developer that is creating actually the solution, writing the Python file, make it that it can run multi-threaded and fast and scale, can just use his or her own favorite tools, use Azure pipelines to deploy it, and deploy it to Azure Container Registry, and later on operations can manage this API as it would manage every API in Azure Kubernetes service. So I want to zoom in a little bit how this custom vision service works. So you have to give it sample data. And for instance, a lot of car icons or a lot of truck icons. So, and you can choose what you want. So you can either take pictures that only contain one object, or, like you see below, you can have a picture that contains multiple objects, but then you have to drag all the bounding boxes around it. So you upload that to the custom vision service, you hit train. If you do object detection, it can train for multiple hours. If you do a classification project with less than 500 images, it is done like in 30 seconds. So classification means I send in an icon, run it to the service, and it will give you like a confidence score. It's saying like I'm 90% confident that it is fake or real. And with object detection, it will tell you, I found a hologram on this location, and I'm like 88% sure that this is actually a hologram. And one of the cool things of custom vision is that you can export your models. So I decided to host it as an API provided by Microsoft. But if I wanted, I can also download, for instance, a TensorFlow Lite model from it and run it directly in the Docker container. So I didn't do that because we were still iterating and we wanted to train and improve very fast, and it seemed like a lot of work to actually export it, get the model, and update all the time the Docker container. But eventually it will be way faster if you run the models locally and not call out to all the APIs all the time. So let's go to a demo and see how it actually looks like. And I see that my VM has decided to stop. So I'm building a little bit of suspense. See that we didn't get any updates. So that's good. We're still here. So this is the custom vision service. You go to customvision.ai and you can log in and you can create a project. So you can create a new project. You click, you give it a name, you say which type you want, the classification or the object detection. If you want to have multiple labels per image, meaning this is an icon and this is a car, this is an icon and this is a truck, or you just want to tag like truck icon. And you can choose a domain. And mostly the general domain works, but if you want to create a food classifier, of course you can click like a base model, food, or landmarks. You see here some domains that say compact behind them, And if it has compact behind them, then you can actually export them, because then they're like a little bit smaller. So first, let's have a look at the Simpsons classifier of an object detection. And I've trained this, this project, this object detection, with like a lot of Simpson images. And to do object detection, you need like a lot of Simpson images. And actually, you need to actually tell them where they are. So I found on the website Kaggle a dataset with Simpsons, with actually all the Simpsons in it. And someone actually tagged where they all are. So I just wrote a small program that just exports it and imports it automatically in custom vision. But that takes like a few hours to train this. So here we see it. And we can, for instance, do like a quick test, browse, select an image where there are multiple Simpsons on it, click open, run it through. And we see that it has found Homer here. It is like 75% sure that Homer is in this picture. Marge is here, Bart is here. And it sees this as Lisa. But it is only 16% sure. So mostly you throw away those low results, because you don't want to have anything that's like 20% sure in your product. So, but what if you want to do this, or from a code perspective, because you can drag and drop images to here, but it is not very repeatable. And you want to have it, of course, in version control, so that you can later on work together on it and actually do it again. So you can do this also from a Jupyter notebook using a Python SDK. And this is a Jupyter notebook running inside Visual Studio Code. So we launched that 4 days ago, that you can actually open and run Jupyter notebooks directly in Visual Code without running your Jupyter notebook servers. So you install this SDK, Azure Cognitive Services Vision Custom Service SDK. We start with importing some packages, and then we have to create a project. And to create a project, you need a training key. You create a custom vision training client, giving the key and the endpoint. So my endpoint is in Western Europe, so you probably want to choose something that is a bit closer, that makes it go a bit faster. And then you can ask for a list of all the domains, because you have to give like a domain ID. And I will just choose general compact, because I later on probably want to export it. But you can change it also later again. So if this domain doesn't work for you, you can choose another domain and see how well it performs with that other domain. And then the only thing to do is start tagging and uploading images. So I'll run this already. So the first thing you have to do is create a tag, upload the image, and tag the image. And you upload images with this SDK in batches of 64 images. So you have to probably upload and divide it into multiple batches. So everything is uploaded, and we have a tag Homer and Marge. And I made this very simple. That is just a directory containing Homer images, and there is just a directory containing Marge images. And then I can train it, start training it. So I run, and it should be done like in 30 seconds. So you never know. So when it is done training, you'll see it later, we have to publish it to an endpoint. So there is an iteration trained, because every time you train it, it creates a new iteration of the model. And that iteration you can publish to an endpoint and use that in your solutions by just doing a simple REST call. And it is still training. It's taking a bit longer today. But yeah, it is also in Western Europe. So we will wait for that a little bit, but I can already show you what it has created here in the visual interface. So we go back here and we see that it has created the Lego Simpsons NDC, because I have a lot of Lego figures of Simpsons, and I took photos from that. And one important thing you have to remember when you take photos of it, you have to take it from a lot of different angles, but keep the level of light somehow consistent and the quality of the photo somehow consistent. So you take it from a lot of different angles, and don't forget to take it with a lot of different backgrounds, because if you always use a white background or red background, it will probably start recognizing the background instead of the Simpson you want to classify. So let's see if it is already done now. It is still training. That is not very good. So let's see what it is doing. Here it is training. So when it is done training, you can start running predictions against it. It's taking really long today. So yes.
So with the predictions, you get a confidence level back.
Yes.
Your earlier example of real or fake.
Yes.
What's the sort of cutoff point? What level of confidence would you consider real, otherwise fake?
Yeah. So in our tests, we saw that like you have to at least reach between 80 and 90% confidence for the icon to be real. So we were constantly like monitoring it and running through tests, and that is the sweet spot we found. But for every model, it can be like different. Okay. Yes. So it doesn't necessarily have to be like 99% sure, but like 20% is definitely like too low. So it really doesn't want to finish training today. So when it is done training, you can run predictions against it. And there is here this cool tab, predictions, where you will see all the images come in, and you can see the results and monitor and tweak your model. So we can see that actually in this object detection thing, and we can go back to predictions, and here we see all the images that came in. So this is probably our image, and then we can see what it has done. So in our project we have like the classification and the object detection. So here we can see everything that came in and see how it performed. So that is really cool. One more try to see if it is finished, and otherwise we will continue. It is still training. So what you will see if it is done training, an iteration will show up here, and you will see how good the model is. See how many images it's been trained on, and you can find the prediction URL, and if you're trained with a compact model, you can export it here and download it here, and you have also access from there to some examples how to actually run this model and pre-process your images for it. So if you want to do this yourself, create this custom vision with my dataset of the Simpson Lego figures, you can go to this URL, and there is this whole big tutorial on how to do it yourself. So then the next thing I want to dive into is the logo classification part. And we tried it to classify the logo if it was genuine or fake with custom vision, but it did not work. So our data scientist decided to train her own neural network on the very specific parts of the Philips logo. So this logo classification is also running in its own Docker container and is available with an API. So we use the computer vision API to scan for the word Philips and cut the word Philips out. And we send that to a pre-processing function that will actually put the Philips logo straight, put it in perspective, and does some color balancing, transforms it probably to black and white, and some more things so that it really stands out. And then we run predictions against it with our model and return the result. And it is also using the same configuration, same version of Python, same version of Ubuntu, and runs in an AKS cluster. So how does it work? First of all, you need, again, a bunch of labeled images. So you need a lot of fake images of Philips logos and a lot of genuine images of Philips logos. So we've done that, and we've also created a lot of fake images and real images using image augmentation by rotating them, flipping them, and changing color, changing contrast. And of course, our intern made a lot of fake Philips logos. We trained our model using Azure Machine Learning Service, where I'll later show how to do that. And then we can deploy the model using Azure DevOps pipelines. And then we have our Jupyter notebooks that actually test the model to see if it was better or worse against our test set. So Azure Machine Learning Service is our fully managed cloud service that enables us to build, deploy, and work together on machine learning projects. And I'm not going to use real data here because training the Philips logo takes, like, the last time we did it, it was about a week to have a real classifier. So I'm going to train a classifier here that, from scratch, that can detect if it is Homer or if it is March, using the same test set we saw in the custom vision. So I have a lot of SimCity images from the website Gaggle. So if you need any data set to experiment yourself, go to the website Gaggle, and there are lots and lots of cool projects you can try and play around with, including this one. So when you start using Azure Machine Learning Service, there are a lot of steps you have to do, and you have to work together to actually get it running in production, because just creating the model is not enough. It also has to perform and run very stable. So first we will have a look at how a data scientist will work. So the data scientist will, of course, want to use their own favorite tools, probably Jupyter notebooks. We will force them to use something as version control. And we train the model in Azure Machine Learning Service, with the deliverable being the model, and the model is being registered in the model management service. A developer can pick up the model from model management and build software like it always builds software. And the model management I see as like the NuGet repository or the Docker container registry for models. So the models are being versioned there, and the developer pulls the model in their solution. And in my case, the developers had to deliver a Docker container registered in Azure Container Registry. And then operations can deploy, as they would always deploy, a Docker container, because it is just an API running and probably needs some GPU, but it is just a Docker container hosting an API. And then, of course, the client can do predictions against that API. So to get started with Azure Machine Learning Service, you have to go to 3 phases. So first, you have to prepare and set up the whole environment. Then you can start experimenting and training your model. And then the final step is actually getting that model safely and repeatable in production. So preparing our environment. You can do that in multiple ways. You can go to the Azure portal and start clicking, and it will create a service for you. You can do that in VS Code. There are AI tools for VS Code. Right-click, create an environment, and it will create it for you. Or you can do it from Jupyter Notebook using the Python SDK. And my preference is that all the code is repeatable. So I prefer to do it in code, in Python, or in Jupyter, or Python running in a Jupyter Notebook. When you've created, it looks like this in Azure. The interface is just updated, like I think 4 weeks ago, and it looks really nice and smooth. So let's zoom in what you actually get when you have created these environments. So you get datasets. And datasets is a place where you can register your datasets, which you can use all over different projects. We have experiments that keep track of our training runs. So every time you train a model, it generates a lot of output, and that is grouped in experiments. We have models, and that is the model management where what I was talking about, and that is where you can actually register your model and pull out your model later if you want to use it. We have endpoints, and there are two types of endpoints. So there are real-time endpoints. This solution can wrap your model up and deploy the Docker container for you in production in an AKS cluster, keep track of everything, and it will register the endpoints, and you can find them back there. But there are also pipeline endpoints. And a cool thing you can do with Azure Machine Learning Service is you can create pipelines. And pipelines are workflows of steps. So you create a lot of separate steps. You always have a pre-processing step, you have an actual training step, and you will have like a deployment and registering step. So in a pipeline, you can chain those steps to use each other's in and output. There is of course compute. So you can manage your AKS clusters from there, or your AI clusters, and your Jupyter Notebook servers. So you can find all your compute back under there, and you can have data stores. And data stores are the reference places to your data. So in my case, my data store is just a simple blob storage. So I can register them under data stores, and then later on access them by just giving them a name, meaning I don't have to check in my credentials. So creating a workspace. This is the first thing you have to do, and you only have to do that once. So you create a workspace, give it a name, give it a subscription ID, give it your resource group, and your location. So in most data centers, it is available at the moment. And then when you have created this workspace, you write out a config file. And later on, you can read in that config file. So you don't have to recreate it everything, you can just check in the config file, and anyone later can load in the config file and work in the same workspace. The second thing you need is compute, because you need something to train your model on. And here I say, create a standard NC6 compute cluster with minimum nodes 1, maximum node 6, and give it this name. And it is creating a cluster. So this cluster will always have one node constantly running, and it will cost me 600 euros a month. If you don't want that, you can put minimum nodes on 0, and then it will only spin up a node when you submit something to be trained to your cluster. So it takes 5 to 10 minutes for a node to spin up, and you can configure how long it takes for your node to go down. So mostly it is like if the node is 10 minutes inactive, just shut it down. So when you set it up, do this well, or your credit cards get really big bill. So and then you need your data stores, and that is also called attached storage. So by default you get a blob storage where you can put everything on, but you can also register every blob storage available in Azure, because most of the time you already have your data somewhere and you don't want to transfer that to another blob storage. So you connect either your default data store or just give like the container name, the account name, and the account key. You only have to do this once, because later on you can access it by just saying the name of the data store. So don't check in your keys in version management. So that is it. If you have these three things, you're done. And then you can start with experimenting with your model and your data. And that is actually where the fun part starts. So to begin with, you have to create your experiment name. So that is just a reference to your workspace, and then you give it a name. And for my case, it would be like Simpsons classifier. You have to create a training file, and this is the file that will actually do the training. So this is a keras file that creates a deep learning model with multiple layers. So this is what typical your data scientist will facilitate or create for you. So you need that file that does actually the training. To run that file, you need to create an estimator. And you can see the estimator as like the configuration for the Docker container where the training process is going to run in. So I say create an estimator from the base image TensorFlow. I point to a script folder, and the script folder is the folder where my training scripts and my other scripts are. I say use some script parameters. In this example, it is only the reference to where to find my data, my training data. In this case, it is just my default storage device. Use this compute cluster, that is the cluster we've just created in the previous steps. And when you're all set up and run, execute train.py. And then the training process will start. The Docker compute container needs to be configured to use GPU. So I say use GPU is true, because I have some GPUs in my cluster. And I can configure which additional Python packages have to be installed on that base image. So I need scikit-learn, I need keras, and I need OpenCV for my training script to run. And you can configure your TensorFlow version. And I'm still using version 1.10. So that is the configuration you need to run that training py on your cluster. And when your estimator is ready, you can submit that estimator to your cluster. It will start up, it will boot up your Docker image, and it will execute the train.py. And then it will stream back the output to this cool widget, and you can real-time follow the log files and the output that training script is providing, and you can even get like real-time data of the performance and the training status of your model. So let's create one. Yes, and my VM is still up. And we see that it is finally done. It took a while, but here we see that I've created a perfect model. It's like 100%, 100%. And if you scroll down, you see that I have 52 images per tag, and that it is quite happy with that. So this I will run from a Jupyter notebook, just running a basic Jupyter server. So I have to install the Azure ML SDK and keras and TensorFlow, of course, locally. And then I will start with importing these dependencies. And there are a lot of dependencies you need. I load in my workspace from a config file because I've already created my workspace. And then I can ask, give me the details from this workspace. And then you get some, like lots of details from everything that is connected to that workspace. So you see where your container registry is. You see underwater it uses a key vault to communicate. So you can actually see where that key vault is located. You can see and find out which service principals it used to connect and with where your storage devices are. So we have to connect to our compute cluster. And you see I have currently one node running from a standard NV6 virtual machine, and my cluster is named NV6 AI cluster. And I connect to my data store. And you see this is just a simple name, so I don't have to be bothered with credentials here. So if I go to my Azure Machine Learning workspace, I see here on the data stores that I have a training data store here. I can click on it, and then you see where it actually connects to and where it is located. And I can change also where it points to from here. So I will go back to my Jupyter notebook, connect to my data stores, create an experiment, and if the experiment already exists, it will not recreate it, it will just load it in. And then I can start creating my estimator. Oh, go back, please. I can start creating my estimator. So I point to the script folder where my training scripts are, and I set up some additional parameters. So I want to mount the data store I've just connected to. I specify that I want to use 64 by 64 images, pixel images. I want to have my batch size is 32, and I want to do 10 training rounds. So that is not enough to train a good model. So you need to have more, but for this example, it will train very fast, hopefully. And so we can have a look. So we can actually run and submit this estimator. And in the meanwhile, we can have a look at this training script. So this training script is like any other training script a data scientist will use. And I actually downloaded this training script from the website Gaggle and put in a few adjustments. So the first thing I added was I added some references to the Azure core, Azure ML core. And then I can grab like the run context from the training round. And the cool thing I can do is when I have the run context, I can create a callback function because this is scarce, and I can use callback functions to actually log things to the run context. So if I log floats from every training round, this is the accuracy from my model I want to log. So if I log integers or floats, it will automatically create a graph for me in Azure Machine Learning service. But I can also log strings or whatever I want. And the thing you don't want to forget, because this is being trained on that cluster, and your training script generates output, you need to get those files, the models that created. So you have to save that in a directory outputs. So everything you save in the directory outputs will automatically be copied to your experiment. So you don't have to worry about the files, but everything else will be thrown away because your Docker container will just shut down and it will be gone. So save it in outputs. So if we go back, we see that our model is starting to train. And that will probably take, well, this one goes way faster. So we see that it has streamed all the outputs from the training rounds. It is run for 1 minute. And here we see the graph from the callback function I just showed. So it creates a cool graph for you. And we can go back to Azure Machine Learning Workspace and zoom in to the latest run because it is logged under our experiment. So here we see it is run. Now we click on the run number, and here we see all the details. So we can go to metrics, and we can click on the accuracy because that is the key where I logged the accuracy under, and we see here that it can create a graph for me. So everything now is in this service, and we can see everything back. And everyone else that is working on this can actually repeat it and read the log file. So that is very, very cool. So what actually happened underwater from there? So you saw me typing in my Azure notebook, and I started and I submitted the job. So it took a snapshot from the directory where my training scripts were located and sent it to the experiment. So everything is versioned there. It created a Docker container based on my parameters, installed the extra packages, and it put that in an Azure Container Registry, so I can use that later on again. So it is not every time you submit a job, it is not recreating the whole container. So if you don't change anything about your container configuration, it will be the same. That is why my training went so fast. If you do it the first time, it will take like 10 minutes to set up all these containers. So it creates the Docker images, and then later on, it deploys those Docker images to my compute target. It mounts the data stores. So all those data stores are just accessible as a virtual directory in your Linux. And it launches the training script. And then when the script is running, it will stream back all the outputs first to the experiment. And then if you want, you can run the widget in your Jupyter notebook and see the output also real time there. And then when it is done with the training, so that the train.py is ended, it copies over the outputs, the models, back to the experiment. And then you can register the model. So if you're happy with the model, you register it, you say, hey, I give it a name, the model is located in this directory, and you give it a description, and you register it. So the model was done, so we can now actually test and see if it is any good. So we continue here, and we say, register our model. So now it downloads the model, and it registers it under this name. So if we go to the Azure Machine Learning workspace, we can go here. We can go to models, and here you just see a list of all my models and the version numbers. So we can click on the model, and we can see what is in there and all the details, when it is trained, how it is trained. So when I have that, I can also download it again from the model store, and I can use it in a local script to test it. So I load in the model, I tell it which characters there are, I open it, I do the same pre-processing on the image as I did while I was training. So I will load in the model, and the model is loaded. And then I have a test directory with around 100 random images of Homer and Marge that were not in my training set. And I will run it, and we will see how it is going to predict. So let's scroll a little bit. So we see that it is right. It is 100% sure this is Homer, Homer, Homer. And let's see how sure it is about Marge. It is even sure that this is Marge. So you see, in like 2 minutes, I can actually run a complete version of training a model in the cloud with my own scripts, with my own framework, with my own configuration.
So that model is a TensorFlow model?
Yes. If you want to train that, that is very well possible there, yes.
Okay. Can I convert that model to a Coronal model?
I don't know how to convert that, but it is just a basic TensorFlow model used with Keras, yes. So, and then you have your model, and then you can actually run it real time against the video. So I've trained this with like all the Simpson characters. So that were 50, and it took me like more than a week to actually train. So I will run the video, and
so, working hard or hardly working? Boy, weaseling out of things is important to learn. Release the hounds.
This is the worst day of my life.
The worst day of your life so far.
Release the radioactive steam!
Lisa's a little young to be taking happy pills.
I'm going to Disneyland.
So have a Merry Christmas, Happy Hanukkah, Crazy Kwanzaa. That's it!
so if you want to do this yourself, I have a whole tutorial how to set everything up, the training scripts, the training data as a reference to Gaggle, of course, and you can do this from scratch and make your own funny video. So I want to have one last point about deploying that model you have in production, because now it is nicely Simpsons, and in my case it is of course a logo that detects if the logo is genuine or fake. So I want to zoom in a little bit about how to deploy it as a developer. So the developer of course uses their own favorite tools, wants to version everything in GitHub or whatever Git repository, and use a build pipeline and register the container in Azure Container Registry. And my projects look like this. I have an app.py that runs a small Flask server. I have a Docker file that has my Docker configuration, requirements.txt that will install my Python packages in the Docker container. And I have my Azure Machine Learning config.json in my repository. So that is the configuration file we've created all the way in the beginning when we were creating our workspace. And I have a download.py. And this download model.py I will run in my build step. So, and this download.py, the only thing it does is use the Azure Machine Learning config file to connect to my workspace and downloads my model into my project. So I can put a specific version, or I can always take the latest version of the model. But the last thing you want is to check your model into source control, because they get like 2 or 3 GB if you have like a serious model, and you don't want to have that in your Git repository. So this is how I solved it. And so, and if you look at my build pipeline, I say use an Ubuntu image, use Python 3.6, and run a shell script. And this shell script will install the necessary Python packages, and it will install the Python package that is needed to use the CLI, the Azure CLI, to connect to my Azure subscription, because you can't give it any credentials. So you use the service principal from Azure DevOps to connect to your workspace. And then I run my download script, it downloads the model, and I start building my container, and my model is there. So a small recap about my project. I used Azure Functions, Azure Durable Functions, to orchestrate the whole solution that is all doing very individual specialized steps. I used custom vision for the easy models. So my advice is always to try and see if there is like a out-of-the-box service that can do the job, because training your own models and setting everything up and running it yourself takes a lot of time. Then I made all my services available as an API running in a Docker container that is doing one very specific task, which I can test without any awareness of the rest of the application. And of course, use Git, CI, CD, and test everything from the start, because if you have to do it later on, implement it, there is never any time for that. So my lessons learned from this: you have never enough data to start with. Apply always DevOps practices from the start, because it will bite you in the ass eventually. And we started looking at this problem as like one big problem. So it helped us really to break it into small problems and solve problem by problem by problem. And of course, like I always say, you have to think big for your solution, but always start small and get your base right for your product. So I want to thank you all for joining me today. If you have any questions, I will be here at the conference, because I don't think we have any time left. And the 2 examples tutorials you can find there, and you can always tweet me and find more samples back on my GitHub. Thank you, and enjoy the last day of the conference.